It has started.
Recording. Shall I go
Yes,
with the sharing now?
sure, sir, sure.
Is it a screen share or applications? There are two
Screen share.
options. Screen share.
Screen share. Yeah.
Okay. I'll go with. Is it visible now? Hello?
Yes, sir.
The screen
Yes,
is
sir. Yes.
visible. What do you see
Yes, it
now?
is.
What do you see?
I can see the slide, dimensionality reduction and overview.
Excellent. Thank you.
Yeah,
So,
sure.
good morning to everyone. I'm very happy to be a part of this 5 days workshop on mathematics for machine learning. My interest is now to let you know how dimensionality reduction can be possible. Probably the speakers who have delivered marathon lectures in the last 3 days, perhaps taken you into vector algebra, space of vectors of high dimension. The question is that, do we really require so many dimensions in representing data? Or shall we find out if any dimension which can be expressed as a linear combination of other, so that that dimension could be filtered out? Or is there any dimension which has a high degree of correlation with another dimension, so that one of the dimensions could be removed from the collection? Or do we have, with respect to a domain application, let it be a face recognition application, could it be a fingerprint recognition, could it be handwritten character analysis, could it be online signature verification? Keeping in mind a specific domain, can we identify only those features, only those dimensions, which are rich in supporting my requirement of classification, or could be a retrieval, could be clustering, right? I mean, keeping in mind the purpose, keeping in mind the goal to achieve, can we filter out some unwanted, or how do I find out some features or some dimensions are really not required? Only some of them are relevant. On what basis do I decide that these are all the dimensions which are really relevant, right? Which are rich enough so that I can work with only few number of dimensions in the features vector instead of working with really a large number of features, so that I will have many advantages. That leads to what is called dimensionality reduction. Higher dimension is a curse, in fact, right? There is a curse of dimensionality. And to overcome that curse of dimensionality, we have to think of certain strategies, we have to think of certain methodologies, right? And by the use of those strategies and methodology, if I am able to reduce the number of features, probably I can work more effectively and efficiently. That's what is the primary importance of this dimension. So my interest is just to go for a attractive, wonderful walk on the corridor called dimensionality reduction, and explaining you basic strategies or basic methodologies of dimension reduction in general, touching upon the philosophical views of this dimension reduction, and as and when need arises, perhaps I may take you into little bit mathematical aspects of the techniques. So let me just take you to a different, move on to a different branch which you have not experienced for the last 3 days, perhaps, because I understood that most of the sessions were on vector algebra, linear algebra, and matrix decomposition and so on. Of course, that's very much required for my lecture. But now I'm just shifting to a machine learning application. I have some images to be categorized. I have collected samples of various classes of species. Once those images are captured, then I go for some pre-processing of those images so that those images would appear in a much appealing way. And after doing such a pre-processing, I go for identifying or detecting something of my interest, like region of interest. And out of that region of interest, I extract the features. Extract the features means I just characterize these images of my interest. while characterizing these images of my interest, I just end up extracting some real values out of those. If I can linearize them, right, whatever the real value, suppose if I end up extracting 100 real numbers from each of these images, if those 100 real numbers representing an image could be linearized, then I can call it as a vector, right? Because those 100 real numbers which I extracted are not semantically associated. Could be a color information, right? Could be a texture information, could be a shape information, whatever it's. But I'm not in a position to associate with them certain attributes, semantical attributes. When I am not in a position to attach with them, a certain semantical attribute, then I have to put them in a sequence. The moment I put them in a sequence, then that 100 numbers turn out to be a vector in 100-dimensional vector space, right? So that turns out to be a point in 100-dimensional, vector space. Now I go for such extraction of such 100-dimensional, let it be n in general. Then I just have got these images or samples of my interest represented as points in n-dimensional space, right? So once this have been represented as points in n-dimensional space, then the handling of these images, the problem of classification of images, the problem of generating labels for these images has thus been reduced to manipulation of vectors, labeling of vectors, clustering of vectors, retrieval of vectors, right? I mean, entire problem of my interest has been reduced to the problem of manipulating only what is called vectors. If I am good at vector space analysis, if I am good at transforming these vectors into different space where analytics could be made easier, perhaps my domain application could be solved in much easier way, right? That is the interest of going with vector spaces, right? So then I have some feature vectors generated. Then I got to understand that, do I really require those 100 features to handle? Or can I selectively choose only 10 out of 100? If I end up selecting only 10 out of 100 features for my subsequent operation, then I need not have to work in such a high dimensional vector space of hundreds. Then I have to work with only a lower dimensional space. I mean, ultimate job is how well I can think of embedding these high dimensional vectors into a lower dimensional subspace. Can that lower dimensional subspace is really a subset of that higher dimension? If so, what is the transformation, right? What is that? Probably by the end of my lecture today, you will come to know that the PC is one such transformation which is capable of reducing the dimension or compressing the data of your interest. 100-dimensional vector gets compressed to 10-dimensional vector without much loss of information. I mean, I have to retain as much as possible the original information available in the corpus, even in the reduced corpus. That's the basic principle of it, right? So then I do dimension reduction. Once I end up with a lower dimensional representation for higher dimensional vectors, I go for initiating learning models. Learning models would understand how two vectors representing two samples of the same class, similar, how two vectors representing samples of different classes to be different. Having understood such similarity and dissimilarity within class and across classes, then my learning model generates a knowledge base. That knowledge base has got to be kept, has got to be reposited with the support of a domain experts in a corpus. And by the use of a suitable indexing structure so that faster retrieval, faster matching can be possible, then I say that my corpus is ready. And corpus can be used for subsequent operations of recognition, subsequent operation of labeling, subsequent operation of clustering, whatever you want to do, right? This is how I create corpus. And look at here, the dimensional reduction happens to be one of the major indispensable component of any learning model. So soon after you created a corpus, and in case if you come across with something which is unknown to you in subsequent days, then inject it to the same sequence of operations, end up extracting 100-dimensional feature vector in specific or n-dimensional feature vector in general, and subject it to the same dimension reduction technique. Then you end up with extracting 10 out of 100 and go for classification. The classifiers would look at the corpus that you created yesterday as a knowledge base, and based on the similarity or likelihoodness of the unknown sample with the samples of the already seen, then you will have some k retrievals with along with rank, score 1, 2, 3, etc., and go for making up a decision whether that unknown sample belongs to class 1 or class 2, class 3, etc. This is what is called a classifiers. Right? Look here, The interest is now on dimensionality reduction. So dimension reduction, probably last session speakers must have explained you that if there are m number of samples, and if each sample is characterized by n number of attributes or n number of dimensions, then I can come out with a matrix called data matrix. That data matrix is of how many rows? M rows, having n number of columns. Now the question is to reduce the number of columns. So that reduction of number of columns is what is called dimensionality reduction. And similarly, you can think of reducing the number of samples also, going with a cluster analysis. When you do, grouping of looking similar samples together, then you can avoid storing number of vectors. So you can choose one vector which is a representative of several vectors together based on their likelihoodness, based on their mutual Euclidean distances. And then I say that it is a cluster analysis. The cluster analysis would help you in reducing the number of samples. So instead of working with n number of dimensions for doing cluster analysis, why can't we think of reducing first the number of dimensions and then initiating the cluster analysis, so that cluster analysis becomes more effective. So this is what is called dimension. The dimensionality reduction is a process of crashing of n features into d features, where d is reasonably very small when compared to n. I have n number of features, n is reasonably a big number, and I have to crash them into only d, where d, when compared to n, negligibly small, reasonably small. And such a crashing process is what is called dimensionality reduction. So the advantages are many. To name few, it helps us in reducing the memory requirement. Instead of storing n number of features, n number of values for a vector, you end up storing only few number of values for a vector, right? And data analytics becomes simplified, and cluster analysis, classifier design becomes much easier. And instead of visualizing the data in higher dimension, it's quite relatively simple when you think of visualizing the data, right? Time efficient classifier can be made, more efficient, more effective, a model could be generated, right? Those are the many advantages of dimension reduction technique, right? Basically, there are two methods of dimension reduction. One is called feature selection, feature subsetting. Probably no speakers for the last 3 days must have spoken about this. And I'm sure that most of the speakers yesterday and day before yesterday and today in the morning must have spoken about feature transformations. Some transformations. Given is a data matrix X, then how do I employ a function F on that, so that F of X becomes something Y, where Y is of different dimension. Right? Look, very simple. I have one transformation T. I have an input data. I just give it as input. The moment I give it as an input, this transformation T transform this n dimension space to a different space. If the transform space is of same dimension, then you are with no reduction, no enhancement. If the transformed space is of higher dimension, you can move from lower dimension to higher dimension also. If that transformed space happens to be higher dimension, then I say it is a dimensionality enhancement. If the transformed space happens to be of input dimension, then I call it as a reduction in the dimension, right? Basically, these are the three varieties I'm talking about. Look, if I touch upon the feature selection to begin with, so feature selection, as the name itself indicates, it is to select a subset of the available. I don't do any transformation. I don't manipulate it. Instead, I selectively choose some out of several available. I'm given 10, out of 10, I have got to select to choose only 3. So then it is a process of subsetting, It's a process of choosing D number of features from a collection of N features. Obviously, it is a subsetting. So that how many D, even I don't know. I have got to maximize my output. In order to maximize my output, I have got to find how many features are really got to be selected. That is still unknown. Then I got to go for n number of features, but I got to generate all possible subsets of n features. When I generate all possible subsets of n features, because of set, from the background of set theory, if it is a set with n elements, then that set with n element has got 2 over n subsets, right? Any one of these subsets, any one of these possible subsets, could be the subset of my interest. Then what I got to do is I got to try with each subset and then evaluate the performance of a classifier. And based on the performance of a classifier, I get to decide, oh, this subset is much better than that. But unfortunately, that 2 power n possibilities are going to be executed. Pragmatically, it is impossible. Then I would look for some method of optimizing it, some method of selectively choosing it, right? So then I got to go with some dynamic programming, some branch and bone strategies, right? Whatever. So you can go with some strategy of selecting a best subset of out of several 2 power n available, right? So this problem appears to be exponential in complexity. Then because of that, we go for some strategies. I'll come to that a little later. Now, what is this feature transformation on the other end? Feature transformation is nothing but this. There is a space called original dimension, original space. Then I don't want to operate my vectors in that original because it appears to be much complex. It appears to be much challenging. Instead, can I take up or move these points in higher dimension to a points in some other dimension, right? So that that manipulation of vectors or labeling of vectors, whatever the operations with which I am interested in, becomes much easier in the transformed space. Then I have to work out a suitability, right, which helps me or which makes the problem analytics very simple in the transformed space. So this is what is called feature transformation. Here in the transformed space, original dimension, original features are not retained. The values are entirely different. Values are generated, values are inferred out of the available input. I mean, here is some real values for a vector. Let's say n in number. These n real values are given as input to the transformation T. This T is expected to compute a new set of values, but the number of values computed by this T perhaps is expected to be less when compared to the number of values given as input to this. Then I say it is a reduction in number of features, right? So that is what is called transformation T. PCA happens to be the principal component analysis, happens to be one such transformation which takes you or which pushes you from higher dimensional space to a lower subspace, right? So here is simple, pictorial way of understanding the notion of feature selection. Look at here on the left hand side, we have a data matrix, call it as, let's say, X. So it is of 6 samples, and each sample is described by or characterized by 10 features. Now I don't want to work with these 10 features. Instead, I selectively choose feature number 2, F2, feature number 5, F5, feature number 9, F9, right? Then I represent N1, N2, etc., N6, 6 samples, not with the support of 10 dimensions, but with the support of only 3 dimensions. And those 3 dimensions, 3 features called F2, F5, and F9 appear to be rich for my application, appear to be more relevant for my task of interest, right? That's why I just ended up selecting F2, F5, and F9. Now, the same X is represented by 3. So now look at the memory required to store X is reasonably less, only 30% when compared to the original requirement, right? And here, whatever you see in the X new, the column number 1 is exactly the column number 2 of the original. And column number 2 of the X new is exactly same as the column number 5 of the original. And the last column in X, the last column in X is exactly what is called same as the 9th column in the original. Okay, so this is what feature selection. I mean, exactly the same values are retained, but not all, only the subset of it. Look, here is an example. Assume that there are 8 samples, and each sample has been described by 3 features, F1, F2, F3. Look at, no 2 samples can be clearly distinguishable, because if you look at S1 and S2, they share the values with respect to F2 and F3. Obviously, when you look at F1 alone, when you look at the F1 alone, none of these could be expressed uniquely, because F1 carries 1 for S1, F1 carries 1, same for S3 also. Then with respect to F1, you will have a confusion in distinguishing S1 from S3, because both carry the same value 1, right? And similarly, S2 and S4 carry the same value 8. And I mean, none of these could be discriminable with respect to only F1, with respect to similarly F2, similarly F3. On the other hand, you try out with the 2 possibility, right? F1 and F2, F2 and F3, right? So which are those, 2 which could be selected? Then I say that you end up selecting only F1 and F3. The F1 and F3 together, mutually together, makes it possible to uniquely identify each of these 8 samples, then I understand that as far as my interest is to discriminate every sample from every other, F2 is of no significance, right? F2 is of no significance. Then I can simply throw away F2, retain only F1 and F3. This is what is called subsetting. I just ended up selecting 2 features. Look at the features which have been selected are present originally as it is, right? So that's why it is what is called feature subsetting, feature selection. Whereas on the other hand, in the case of feature transformation, look at the same 8 samples have been described by these F1, F2, F3, and no one alone is sufficient. And even if you look at the 2 features at a time, right? F1 and F3. When you look at F1 and F3, so look at S1 sample and S3 sample. So F1 value is 1, F3 value is 6. Even with respect to S3, F1 value is 1 and F3 value is 6, right? So even if you go with these 2 F1 and F3, you cannot distinguish every sample from every other. If you go with the F1 and F2, then 1 and 15 and 1 and 15 for S5 is also there, right? So even with respect to the pair F1 and F2, you cannot distinguish. If you go with F2 and F3, you cannot distinguish S1 and S2. Look at, because both of them carry the same pair, 15 and 6 and 15. I mean, now inevitably I have to retain all the 3. In this example, subsetting doesn't work at all, right? However, possible subset, I just go with that, and no subset of these 3 features, right, is capable of distinguishing every sample from every other. Therefore, transforming these 3 into preferably 2. Okay, let's assume that there is a transformation T. I'm sorry, am I audible?
Hello. Yes, please mute your mic.
Some disturbance.
I request all the participants to mute, please. There is a background noise. Yeah. See, what we have thought of is that, just apply some transformation T and give these 3 values, the 3 values associated with S1 as input to that, and let this T generate 2 values out of those 3. I mean, let this T integrate all these 3 values together and then generate 2 components. Let's say small f1 and small f2. So for S1 sample, 41 and 1458 got generated. Let's assume that. Now, when the 3 characteristics of S2 have been given as input to this T got us generated other 2 values for S2. Now, for every sample here, T has been employed and correspondingly the pairs have been generated. Look at now, using these 2 values, F1 and F2 in the generated, transformed space, I can distinguish every sample from every other. Then instead of working with these 3-dimensional data, subsequently, you can just continue working with only these 2-dimensional data. Look at these 2-dimensional data are not originally present in the original, the pop data matrix. They are transformed. They are inferred out of these 3. I mean, the 41 associated with the S1 with respect to the feature number 1, it's not something generated out of F1 here only. It's not something generated out of only F2, only F3. It is because of the integration of assimilation of using some, methods of mixing up those with their own, weightages, some certain weightage of F1, certain weightage of F2, certain weightage of F3, and then doing some mathematical operations on that, T got us this 41 generated, similarly 57, similarly 1458. I mean, even the value which has been generated is because of the application of the transformation T. In this example, the transformation that I have used is simple transformation with which you're all well familiar. I mean, I just assumed that this S1, the features 1, 15 and 6 as the coefficients of a quadratic equation, ax square plus bx plus c equal to 0. So a equal to 1, b equal to 15, 6, c equal to 6. Then I just thought of assuming that S1 is nothing but x square plus 15x plus 6 equal to 0. Having understood that it is a quadratic equation, I just got the roots obtained, and those roots in a scaled version have been displayed in the right hand side, right? Look at, I mean, what the T is a quadratic solver. Here, all the 3 input values are assumed to be the coefficients of a quadratic equation, and the respective roots have been generated, and those roots have been displayed with the scaled version, right? Look, quadratic solver can also be exploited as a beautiful, transformation technique to move from 3-dimensional to 2-dimensional, right? So quadratic equation solver takes 3 input value, right? I mean, whatever the algorithm you must have developed in your first semester of graduation itself called, write a program to solve a quadratic equation. That quadratic equation solver takes 3 input. I mean, the input space is 3 dimension. It generates 2 output. I mean, the output space is 2 dimension. I mean, quadratic solver takes you from 3-dimensional space to a 2-dimensional space. Now, you just got 1 dimension reduced. And that is what is called dimensionality transformation. I mean, feature transformation. Look, this is very simple. Look at this cube, the corners of this cube. And however you try, onto any plane, right? It could be XY plane, it could be YZ plane, it could be ZX plane, whatever the plane on which you try to project this cube, I'm sure that the 4 vertices would go and lie on the other 4 vertices, right? If you project this way, these 4 vertices will go and lie on the other 4, and if you project this way, these 4 vertices corners would lie on the other 4 corners, and so on. I mean, whatever the 2-dimensional plane you are thinking of in this conventional XYZ coordinate system, you cannot distinguish all 8 corners. You cannot identify all 8 corners uniquely. Instead of that, can you relocate yourself? Instead of standing at the origin O, if you can relocate yourself and look at all the corners so that all corners become visible for you, then probably you can map them onto 2-dimension, and that is what is being done by this quadratic solver, right? Look at on the right hand side, I just have given the scattered point of those 8 which are uniquely identifiable and which do have their own magnitude and direction from the origin in 2D plane. Hence, if the moment is 3D to this 2D, every vertex of that cube becomes distinguishable with only 2 coordinates. I mean, I just have reduced 1 dimension. This is what is the philosophy of feature transformation, right? As Professor Nagbhushan rightly pointed out that, so yes, I have a magic box. What does that magic box do? I give certain input, it generates certain output. That generated output are supposed to be something which is not created. It is inferred out of available. It is integration. It is because of assimilation. It is because of agglomeration of all input together into some version. That's what is called output, right? So I just have given 3 input, got the 2 output generated. Now I understand that these 2 values are really rich in discriminating everyone from every other. Then I'm happy with that. I need not have to concentrate on 3. I got to work with only 2 in the subsequent stages. That's what is the philosophy of what is called a magic box in between modeling, right? One is thinking, using of the mathematics, exploit the beauty of that mathematics, go for programming it, model it. The moment you model it, you need not to worry about give input and take the output, then works like only a black box, right? So feature selection method, if I just touch upon now, basically we have the following 2. One is a filter method, the other one is a wrapper method. Filter method, as the name itself indicates, like a coffee filtering, right? What do? The moment you prepared a coffee, you just go for filtering it up. The moment you pour the coffee onto the filter, then filter will allow only required coffee to pass through by blocking the dust particle. Similarly, in the filter, I got to think of some strategy where I keep all the dimension over here. The moment I keep all the features over here, then it allows only a couple of them to pass through by blocking the rest of them, right? Then, which are those which are supposed to be selected? That is what is called depending on the learning algorithm, right? Independent of the learning algorithm. So look, filter method works independent of the learning algorithm. I need not have any knowledge on which learning algorithm I would be employing in subsequent stages. I just go for deciding these are all the features which are relevant for me based on some feature selection criteria. I got to think of, or I got to first fix up, this is what is the criterion which is supposed to be satisfied by a feature, by a dimension for its selection, right? Similarly, exactly like selecting students for master's education. So there are thousands of applicants, BE graduates, who apply for master education in my institution, but I select only 20. On what basis? I just fix up some criterion. Whoever who meets with the criterion and becomes the top scorer, then only top 20 students will be selected for admission. Similarly, here in filter method, irrespective of which learning algorithm, irrespective of who would be teaching them, I don't worry about, I don't bother about the teachers who would be offering courses for those selected students, but I just end up selecting 20 students first, right? And such a method of selecting the dimension or the features is what is called filter. I mean, filter method works independent of learning algorithm, right? And it works based on a feature selection criteria. Wrapper method works dependent on the learning algorithm, and I will decide who is supposed to be the best student knowing about who is the teacher offering the course, right? I mean, if selection of student is completely driven by the teacher who would be offering the course for them, then I say it is a wrapper technique. Wrapper technique which wraps around a learning model. I must first fix up which is the learning algorithm that I would be employing after feature selection, and see that the feature selection is completely governed by the characteristics of the learning algorithm. And such a method of selectively choosing the feature is what is called wrapper method, learning algorithm dependent technique. And here I needed to go with feature selection criterion, I got to go with performance criterion. And if I select these features, what is the performance of, how does this learning model perform? Right? If I select another subset, how does it perform? And depending on which is a subset which really leads this, which makes this performing better, I got to select it. That's what is called a wrapper method. Strictly speaking, there is nothing like a pure filter, pure wrapper. Generally, we hybridize them. I mean, combine filter and wrapper together for effective way of selecting. And sometimes I go for combining multiple feature selection criteria and together into single. That's what is called ensemble. Multiple, wrapper methods together into single, then I call it as an ensemble technique, right? So if I just give you the philosophy again, filter method, as I said, look at, there are all features given, and I have to work out some strategy for subset selection and do evaluation of each feature. Whatever the feature which is evaluated to be high score, then that features will be generated. In fact, even in PCI I do indirectly. While transforming, I end up selecting the best. PCA is not only simply transform, it also does indirectly a filter method, right? So we'll come to that, we'll come to know that little later. So look at on the other end, wrapper method. Wrapper method works depend, in wrapping around the learning algorithm. I mean, given as n number of features, and that n number of features will be, given as input to the system, and system performance will be calculated, and then again one of the features will be eliminated, again system performance will be calculated. If system appears to be performing better than the previous, then I say that whatever the feature I just have left out, appears to be irrelevant, I can go with n-1. Again, I think of leaving out certain, and then evaluate the learning model. If learning model continue performing better, then whatever the feature I just have left out appears to be not required, right? This is how I go for wrapping around a learning model, right? So here in learning, wrapper method, I get to have a thorough knowledge on learning model, and I must have something in hand. What is the performance measure which is supposed to be used to evaluate each time, when I conduct the experiment on different subsetting of features, right? So that's what is the difference between filter technique and a wrapper technique. Again, I am stressing upon, in filter technique, I just decide the sequence of features. I just rank the features independent of who will be working on it. But whereas in the case of wrapper technique, while ranking of the features, I must have knowledge on what learning algorithm would be employed, right? That's the basic difference between these two. So filter design is quite interesting. So nowadays, because of high dimensional data, most of the time feature transformation techniques are practically not feasible.
Sir,
right?
can you give the example for both the say things, say feature
filter
selection
and the wrapper, filter and wrapper.
Yes. Can you explain with
Yes,
example?
suppose assume that there are two teachers, there are two teachers who offer the same course called data structure, right? So there are two teachers who are offering the same course called data structure, but one teacher teaches the data structures from the point of view of mathematics. One teacher teaches the same course called data structures from the programming point of view. Then who are the best students to attend these two teachers, Then I say that I go for selectively choosing only those students who love mathematics for the first teacher, and I selectively choose only those students who love programming much, for the teacher number 2. Then I say the student selection is purely not based on their performance, but based on the teacher's interest. And such a selection is what is called wrapping. Whereas in the case of filter design, the conventional, selecting students for admissions for master's degree, we just rank them based on their qualifying examination, right? 1, 2, 3, etc., and choose top 10 students for admissions, irrespective of the ability of the teacher, right? Irrespective of the expectation by the teachers. That's what is called filter. I'll come to that, in later slides with the specific technique,
Thank you, sir. Now,
okay. So look at here in filter design is basically 2-step. One is select the relevant features. How do I select the relevant features? There are n number of features. Then use some dispersion measures. For example, here assume that there are n features. What do? I got to have some method of computing the relevancy score for each feature. For example, there are 100 cricketers in India, but I got to selectively choose only 11 cricketers to make Indian team, right? There are 100 cricketers. Out of 100, I have to choose only 11 cricketers. Then I just rank those cricketers, right? I just rank those cricketers. So Sachin Tendulkar occupy the first position, Mr. Dhoni would occupy the second position, Sehwag would occupy the third position, Dravid would occupy the fourth position. It's on that. Then I just rank them according to some score, looking at their batting score, looking at number of catches, looking at their number of the wicket they have taken up so far in their life. Based on those, I just rank them in sequence. Once that such scores have been computed, you just reorganize them, sort them, right? Based on the score, you just sort them. Once those features have been sorted, choose top M. If you want M, you choose top M. If you want 11 cricketers, choose 11 cricketers. Unfortunately, what happens when you ended up selecting 11 cricketers, all 11 may be the batsmen. Then that doesn't turn out to be a good team, because out of 11, at least I expect 5 to be the bowlers, at least 1 or 2 to be the all-rounder, right? But he may be very relatively poor when compared to others in batting, but he is good at fielding, good at keeping, good at what is called bowling, right? Look at which is the best Indian team. The best Indian team is supposed to be the one which involves all. I mean, look, sometimes you understand that number 1 is really required, but number 2, though appears to be ranked number 2, but he is redundant with respect to number 1. Then what I got to do is, I got to selectively choose only few out of M and then bring in some more, though low rank, but still they are expected to participate in a better way in this collection. Then what I got to do is, first, of course, I got to use some degree of dispersion, a measure of dispersion, like mean absolute difference, like variance, like arithmetic geometric mean ratio. These are all some criteria to be used. Mean difference, Fisher's ratio, right? These are all some criteria to be used in order to rank the features. Once these features have been ranked and top M have been selected, then you go for eliminating redundant, right? Look at, I make a members, but unfortunately the third member appears to be redundant when the first 2 members are present, because third member always follows the opinion given by the first 2 members. In that case, the third member appears to be, you better bring in the 4th ranked one, right? Look at, then eliminate the redundant feature. For eliminating the redundant feature, as I mentioned in the beginning of my lecture, you have to first look at, is there any correlation? If there is any correlation between 2 features, then one out retaining the other feature, right? Find out if any such redundant features and reduce further M features. For the purpose of eliminating redundant feature, you can go with a similarity measure like cosine similarity, like correlation coefficient, right? So this is a philosophy of feature selection, especially 2 steps in filter design. Okay, so I mean, I have got 11 players, but unfortunately there are 8 batsmen and only 3 bowlers. But I have to bring in 2 more bowlers into the team. The moment I bring in 2 bowlers into the team, the number of players in the team becomes 13. But I don't want 13, I want only 11. Then I have to throw away the 2 batsmen. Though they are relatively of higher ranked persons, when compared to the people who are now brought in, I got to throw them out because they are redundant with respect to the other batsmen. This is how I got to go with a filter design. But in filter design, I am not concentrating, I am not focusing on whether I am preparing Indian cricket team for playing against Pakistan or for playing against Australian cricket team, right? Independent of that. Independent of the opponent team, I just ended up selecting 11 Indian cricketers. This is what is called filter way of selecting, right? Filters. On the other hand, I'm sure that I'm selecting Indian team to play against only Pakistan team. Then I look at the caliber, I look at the abilities, I look at the performance of every individual Pakistan player. And based on them, I select the best batsman, the best bowler from Indian team, right? And then I say the Indian team has been selected, not independent of opponent team, but dependent on the opponent team. And that is what is called wrapper technique, right? Philosophy. So look, on the other hand, you can also do the following. You take all n features, do clustering of features. I mean, instead of generating the score, you just identify the features which look similar and do clustering analysis. Reduce the number of features n to some number of clusters, right? Do agglomerative clustering, do partition clustering. If you want d number of features to be selected, do d clusters. You run k-means algorithm where k equal to d, right? Then you end up selecting and end up, d number of clusters. From each cluster, you select the cluster representative. Look at here. So the cluster number 1 is F31 and F14. Out of F31 and F14, retain one of them. And from another cluster, F3, F4, F21, identify F3 and retain F3. And retain F8 from the other cluster. And from each cluster, choose only one representative of those features. So this is what is called F4 is retained, F8 is retained, F31 is retained, something like that. From each cluster of features, only one feature is retained. If this retained feature happens to be originally present, then I say that your method is what is called feature subsetting, right? And you got them selected independent of the learning algorithm, hence it is called filter design. In case the class representative, cluster representative happens to be average of all, right? Happens to be the mode of all, happens to be the median of all, right? If you transform them into a different vector and that transformed vector is retained, then I say that you just have employed feature transformation, not feature subsetting, right? And while selecting these features from each cluster, if you look at the learning algorithm, right? The nature of the learning algorithm, if it is Bayesian, or if it is KNN, or if it is support vector machine, right? If it is some other algorithm, then based on the nature of the clustering, the learning algorithm, if you go with selectively choosing the feature, then I say it is a wrapping technique, right? So wrapper technique basically works with a forward selection or works with the elimination, like choosing multiple choice question. How do I select? There are 2 ways. One is if I know the answer, I straight away take it. If I don't know the answer, I go for elimination, right? Similarly, here in wrapper technique, basically we have 2. One is forward selection, other one is a backward selection. Forward selection works with the principle of inclusion, whereas backward selection works with the principle of elimination. That's the difference between them. So you can think of ensembling of forward selection with backward selection together, right? Or you can even think of hybridizing any of these, a wrapper technique with a filter technique. So the forward selection works based on the principle of a method of inclusion. Initially, it starts with the empty set and goes on adding up a feature at a time, right? Feature at a time. At each step, it adds the best feature such that the performance of the learning algorithm is maximized. Every time when I add up a new feature, I expect learning algorithm to work much better than the previous. Or in other words, see that whatever the feature that you add up would boost up the performance of the learning algorithm. Then finally, when you understand that no more feature can be added up, still maximizing the performance, you stop doing it in the subset of it. Okay. So this is how it looks like. Initially, let's assume that there are 5 features and nothing is selected, and the features left out are 5. Now take up the feature 1.
Sir, your voice is breaking.
Hello? Hello?
Voice is
Can you hear
breaking,
me
sir.
now? Hello? Can you hear me now? Hello? Hello? Am I audible?
Yes, sir. Yes, sir.
Okay.
Now it is fine, sir.
Pardon?
Now it is okay, sir.
Oh, fine. Look at, there is a feature F1 selected. Once F1 selected, I just evaluate the performance of a classifier. Then classifier works with a property of, let's say, X1, performance rate is X1, which is greater than the previous performance. Then I retain the F1. Then what do? Again, I think of adding up F2 with F1 and evaluate it, F3 with F1, evaluate it, F4 with F1, evaluate it, F5 with F1, evaluate it, and I tried 4 times. Amongst those 4 attempts, which subset has made that classifier working better, and that is retained. F4 is retained. Assume that now the learning algorithm has a performance of X2, which is greater than the previous performance X1. At next level, do the same thing. Add up one feature, try out with the experiment, add up another feature, evaluate the learning algorithm, add up the next feature, evaluate the learning algorithm, and now try to find out which is the best feature to be added up into the already selected set, so that the enhancement, performance of the system is enhanced. Now F5 is added up, retained F2 and F3 still. Again, at the next level, however effort you put in, whether you add up F2 or add up F3 or add both, it doesn't improve the performance of the learning algorithm. Then you understood that if nowhere relevant, then only these 3 only ended up selecting these 3 features. I mean, these 3 features are selected dependent on the learning algorithm. Look at, for the decision, you just have made use of the performance of learning algorithm. Unfortunate that in the case of wrapper, look at wrapper technique is supposed to work better than any filter technique, because you are selectively choosing the features dependent on the learning algorithm. You select only those which make your learning algorithm work for its maximum, right? Hence, obviously, wrapper technique is supposed to work much effectively than any filter technique. But unfortunately, while selecting those features, you are going to repetitively evaluate your learning model that consumes reasonably a longer time. Hence, practically, it is not feasible. That's why filter strategies are being recommended today. And when compared to feature transformations, though feature transformation techniques are expected to work.
Sir, voice is not clear.
In a subsetting, then.
Sir, voice is not clear.
Hello?
Lot of disturbance and breaking. Voice is breaking.
You are audible. You are audible, but there could be some network problem in between, right? Hello? Hello? Is it fine now?
It's now okay,
Yes,
sir.
it is fine. Fine. Okay.
Yeah.
Okay. Now okay.
Okay. So look at, this is how in the
Sir,
backward
sorry to
selection,
Sir,
it is method of elimination. Starts with all features. At each step, you go for eliminating a feature so that performance of a learning algorithm is maximized. I mean, with all n features, assume learning algorithm performs with 80%, and if I eliminate one feature, learning algorithm performs with 82%, then better to go with elimination of it. And in case if elimination of a feature further reduces the performance of that, don't eliminate it, keep it inside, right? And try with possibilities, and then end up with only a subset of the features of your interest. This is what is called backward selection, right? Okay. So hybrid method is a
forward selection, and wherein we can use reverse backward selection. Sir. In which places we can use forward selection? In which
I will come to that. 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 Okay. Look at in hybrid, what you have to do is combine filter method and a wrapper method together. That's what is called hyper. So whereas in case of ensemble method, it's a combination of same. Do feature score, do testing, do entropy, do variance, combine, generate the combined score. That's what is called ensemble method. Okay. So this is the difference between sequential floating forward and sequential floating backward selection. One works with inclusion followed by elimination, whereas this is elimination with inclusion. Please remember that these two, forward and backward selection, appear to be dual. I mean, one works in the reverse of the other, but unfortunately end result may be different. I mean, though appear to be dual, strictly speaking, they are not duals. I mean, if you have a same domain, same data set, if one works with a forward selection, another works with a backward selection, because this forward selection and backward selection would not end up generating all possible subsets. For selecting the best subset, it generates only few possible subsets, right? And because of that, the end results are the subset which got selected by these two methods may be entirely different. Don't expect the same result. You are going to try out for your population, data population, and see which is really pragmatically working fine when compared to the other. That's what you are going to empirically fix it up. So here is some one image analytic example for you. So here we just have taken up 5-class problem, right? It is into medical image data analysis. The class labels are immaterial for me. Let's assume that there are 5 classes, 1, 2, 3, etc. 5. The number of samples considered for in each class are displayed here. And totally, we just have extracted 4,182 global features, like color features, texture features, RGB histogram, features, etc., etc. All put together, there were about 4,182 global features. So instead of using these 4,000 plus features, can we go with selectively choosing? Then we employed, calculated accuracy, precision, recall, F measure without feature selection. This is how the performance of learning algorithm, right? So these are after feature selection with MED, with MM, with AMGM, with variance, right? These are all the different. Look at using, MED method. We just got 3 features selected. With respect to 3 features, the performance of the system is much better than the original, right? Much better than the original. So look at MM with only 3 features, variance with only 3 features, AMGM with only 8 features. Look at 3 features are reasonably good. They are rich enough in accomplishing the task, but we need not have to go with 4,000 features. I mean, the dimension of 4,000 plus. A vector of dimension 4,000 plus has been reduced to only triplet, and these triplets are good enough to classify these 5-class problem, identify the samples of these 5-class problem without losing any generality, without loss of any classification accuracy. That's what you have to understand. This is a comparison. Another, because of this COVID-19, as a part of our laboratory work, we were in the position of deploying face recognition system. Earlier to COVID, we deployed, a face recognition model in real-time application for thousands of subjects, right? Those the system was trained for faces without mask, but unfortunately, after COVID-19, people started coming with mask, right? Then obviously, face is not fully visible, and because face is not fully visible, the system used to generate, wrong results. So system now is expected to work with the mask also. Then what we have done, we just have retuned up this recognition system, a face recognition system, by doing feature analytics. Look at here. First one is we have to decide whether face is with mask or mask. I mean, detect the face and then identify whether there is a mask or not. If there is a mask, then we are going to selectively choose only those features which are concentrating on the top part of the face, without which are not representative of this mask area. Look at, initially we just have gone with 128 D features, and out of 128 D features, our interest was to select only the subset of these 128 features, maybe 17 number, maybe 16 number. We did not know, right, how many features are really relevant representing this top area of the face, right? We did some feature analytics. Look here, this is what the face without mask. This is what the face with mask. This is the face of a kid without mask. This is the face of a kid with mask. When the kid appears with this mask, we wanted 128 features to be extracted from the face image. Once it is scrapped, extract the 128 features, and then out of 128 features, we have to throw away those dimensions which are representing that mask area, and keeping only those dimensions of those 128 feature vector representing the top area of the face, so that recognition becomes still possible, right? Then we did some work on feature subsetting, right? For that feature selection, we used mean as a criterion to select. We used mean difference as a criterion to use variance as a criterion. We used max difference as a criterion to select. Look at, when we worked with all 128 original features, the system was performing with 81.5% of accuracy. At the moment we had gone with only a subset, selecting 90 relevant features based on this measure, the system started working with 90%. There is a considerable improvement. Look, when we work with max difference 89 as a criterion, 75 features got selected. So max difference 63 feature got selected. Look at, all these features are originally present. It is feature subsetting. But here ranking is done independent of learning algorithm. Together single ranking, out of these 128 features, only 74 features got selected, giving rise to 92% of accuracy. There is almost 11% improvement with only 74 features. Rest of them are representing mouth area of a face, which is of no relevance, because all faces of different people would appear to be same when they come with a mask. So this we have deployed, and later on we just have improvised the performance of system and deployed it in real with 100% accuracy. Now system is working with 100% accuracy for thousands of employees, whether they come with a face mask or come without face mask. Now let's move on to feature transformation technique called principal component analysis. So in this principal component analysis, the fundamental questions which we would be answering are the following. Is there any representation better than the original coordinate axis? Is it really necessary to show all the dimensions, right? Very simple, the questions which I already risen up, What if there are strong correlations between the features? If there are strong correlation, then eliminate those features, retain only others. How could we find the smallest subset of large dimensional space that keeps the most information about the original data? I mean, soon after transformation, I don't like to lose any information. I'm supposed to retain as much as possible the information being preserved even in the transformed domain. That is, which is the best transformation? Perhaps the solution to these questions is principal component analysis. In principal component analysis, we are looking at orthogonal projection
is not
of
clear,
data.
sir.
Hello? So in principal component, you want me to give more volume? I think you can give it in your, raise your volume in the computer, right? Am I audible first of all? Hello?
Audible, sir, but when you are teaching in between, it is disturbance.
Probably it is a network problem, madam, right?
Okay.
Oh, that the institution has to look at the Wi-Fi network in their system, right? Okay. Is to project the original data onto dimensional substrates. By doing so, I have to recompute the basis vectors. Recomputed basis vectors usually orthogonal projection of data to the dimension that maximizes the variance of the projected data. Look at here. We have these dots that are colored. I just got these projected onto this. Look at this purple line. So these are the projected points. So once these points have been projected, I expect these projected points to be with high variance. Ultimate job is to find which is the direction with which the variance in the population of the data could be maximized. I have to look for such a direction. Once such a direction is fixed up, then project the data onto the direction and take these projected values as a representative And ultimately, irrespective of the number of dimensions with which you are initially working, I just want to work with a single dimensional subspace. Then I'm looking for a straight line and I'm looking for a direction on the other way around, where the moment these points have been projected onto that line, I want still separability among the projected points. If I expect the separability even after projection, then obviously it is supposed to be the line which preserves maximum variance in the population. Ultimately, the principal component analysis tries to find such a best fitting straight line, right? And on the other hand, the moment you got them projected, I don't expect the distance between or sum of the distances between the original point and the projected point, this line and this line, the distance of this line, the length of this line, right? The distance between these 2 points. Add up all, I expect average distance, average distance of original points and points to be as minimum as possible. Look at the principal component analysis. Try to optimize 2 things. One is variance of the projected data. Another one is the mean square distance between the original data points and the projected data points. That is what is the basic strategy or basic principle of principal component analysis. Look at here. In the top left, there is a graph. You see the dots in blue color, right? Those are all the original points. And there is a straight line in red in color, right? And each blue points have been projected onto the straight line. When you look at these, projected points which are red in color, they have got certain variance, they have got projected points have got certain variance. And on the other, look at the right or look at the left bottom figure. In the left bottom figure, there is another line with a different direction or a different slope. Okay. Now again, we got these blue data points projected onto that line. The moment those have been projected onto this line, look at the red points here. And now, when compared to the first figure, these red points are with less degree of variance. Whereas in the first figure, they are more upward, right? The scattering is high in the first figure, but the scattering is less in the second figure. And not only that, look at the distance between the original point and the respective projected point. Look at the distance between the original point and the respective projected point and sum them over. This sum is reasonably less when compared to this, right? I mean, the first figure appears to be much appealing than the second one. I mean, this direction is a best direction comparatively. This direction is preferred to this direction for the purpose of projecting. If I want to work in single dimensional subspace, instead of working in this 2D, I prefer this direction rather than preferring this direction. Similarly, this could be another direction. This could be yet another direction. In simple terminology, imagine that there is a set of points scattered across in 2D. Neither x direction alone work better, neither y direction work better, but I have to randomly fix one direction, so that the moment these data points have been projected onto that line, the projected data points will lie on the straight line to the maximum possible scattering. I mean, I want the direction to retain as much as possible the variance. I mean, soon after projection, that projected data is expected to preserve the maximum variance in the population of the data, right? And which is the best direction? Look, the principal component analysis tries to find such a direction so that soon after projection, the data would preserve the maximum variance. Look here. Pragmatically speaking, it tries to rotate the axis and tries to find which is the best direction so that I can optimize 2 criteria. Number 1, the variance of the projected data point is maximized, and number 2, the sum of the distances of the projected point and the original point is minimum. Look at here. I think you can visually understand which is the best direction. Probably the moment that line comes to this direction, line comes to this direction, it has a maximum variance, And not only that, it has a maximum variance. That distances, the sum of the distance between the original point and the projected point becomes as minimum as possible. Look at, now the distance is too long. Distance is, the length of this line is too long. Now it becomes minimum, right? The sum of those distances, I mean, should be made minimum. It has got to optimize two properties then, right? The principal component analysis tries to find such a best fitting straight line. In case of two-dimensional, it tries to find first one and then possibly the second one. In case of n-dimensional, it goes with n such orthogonal basis vectors, so that this original data points could be projected onto each of those orthogonal basis vectors, and those basis vectors will be ranked 1, 2, 3, etc. depending on the degree of variance that each basis vector would preserve in the data population, right? I mean, consider a data matrix X of size m cross n. I mean, I'm talking about m number of samples, where each sample is characterized by n number of features with column-wise 0 empirical mean. I mean, every data sample is now made a mean-centric. I mean, just calculate the mean of all the data samples. Take away that from each sample. Just subtract the mean vector from each of these vectors. Assume, again, I'm repeating, I'm working with n-dimensional vector. N-dimensional vector, there are m such vectors. Now what do? I calculate the mean of those m vectors, and that mean vector is subtracted from each of these vector, right? Each of these vector. The moment you have done it, then I say that now my data matrix or data set has become mean centric, right? Now find the weight matrix, a projection matrix. Because principal component analysis is nothing but a linear transformation. I am trying to find a matrix W, right? A weight matrix W of size n cross D, where D is reasonably less when compared to n. So that lower dimensional compressed representation Y can be generated as X into W. X is of dimension, X is of size m cross n, W is of size n cross D, nn goes cancelled, then Y becomes m cross D. Now Y still has m number of rows, where each row represents the respective sample, but instead of having n dimension, it has got d dimension, where d is smaller than n. This is ultimate. I mean, PCA tries to find this weight matrix W, right? You can relate this with your neural network architecture. If somebody has spoken out about neural network and then linearization of them in the previous day. So where the column vectors of W, W1, W, how many column vectors? D column vectors. Where each column vector W1, W2, etc., WD are of how many values? They are of n values, right? Are orthogonal. I mean, they are mutually perpendicular, and each one of them is expected to be a unit vector. I mean, the magnitude of these W1, W2, WT, D is supposed to be 1. Or in other words, look at any I, Wi, any Wj, as long as I and j are different, this Wit, I mean, the dot product of is supposed to be 0. And the dot product of any vector, this basis vector with itself is supposed to be 1, because it is expected to be a unit vector. Look, finding out such a W, meeting with this requirement, is the primary target of principal component analysis. So with respect to, let's assume that I go with 1 by 1. So if I work with the first column vector W1, it's supposed to be the one which retains maximum variance, right? I mean, the W1 aims to maximize the first coordinate of the projected data in one-dimensional subspace. Think of, for the purpose of understanding it in an easy way, assume that I am working in a 3D space and I have got m number of points, and where each point is described by 3 values. Now I got to fix up some direction, some line in the 3D space, fix up some line in the 3D space. The moment these data points have been projected onto it, these projected data points are expected to scatter with high degree of variance. I mean, this is a 3D space, Similarly, I can think of 3 basis vector. Amongst 3 basis vector, I am talking about the first basis vector, the top rank 1 basis vector. The top ranked direction is supposed to be the direction where the moment these data points have been projected onto it, those projected data points are expected to preserve the maximum variance, right? Once this information preserved by this basis vector is eliminated from the original point, then you have reduced 3D to 2D because you end up with the remaining 2. Again, you select the next one. Again, you select the next one. That's how you can go further one by one. If you understand how do I select the first one, the similar strategy can be used for the subsequent. So now, in general, if it is n-dimension, if it is n-dimensional space, my interest is to project these n-dimensional vectors onto a single dimensional subspace. The moment these points have been projected onto that single dimensional subspace, I do expect the projected point to preserve a maximum variance. I mean, look at, if W1 is such a direction preserving maximum variance, then I understand that the variance is given by what? The variance of the projected point. What do you mean by projection of a vector onto another? It's a dot product of 2 vectors, right? So look, xi is a sample vector, row vector. W1 is a column vector. You can just multiply. Multiply means it's a dot product then. Like this, it's a dot product. So you just square it up. I mean, because it's a mean centric, the mean is taken out. Hence, this is nothing but a scalar version of a, if you divide it by number of samples, m, 1 over m, then is exactly a variance, right? Okay, it is a scaled version of variance. So this sigma xi w1 square has got to be maximized. I am looking for a w1 a basis vector, a w1 a basis vector, such that the sigma of xi into w1 square becomes as maximum as possible. And this xi, where sigma runs I equal to 1 to m, is nothing but a entire X matrix. So x into W1. X is a matrix of size m rows and n columns, whereas W1 is a column vector consisting n values. Then you can multiply, you can generate another n value, sum them up, right? That's what I mean. They square it up, calculate the variance xW1 square. That xW1 square can be written as W1 transpose x transpose. It is xW1 into xW1. Then you have to take this side and transpose it so that the dimension matches, right? W1 transpose x transpose x and W1, and that's equal to, let's say, W1 transpose, retain it as it is, W1 you retain it as it is, x transpose into x, let me call it as S. S is a matrix which is nothing but the product of a data matrix X and its transpose. Here this S is called the covariance matrix of X. I want, look at this V1 to be maximized. I got to work out the weights for this W1 such that this V1 is maximized, where here V1 transpose into S and to W1. Perhaps somebody must have spoken about this representation in the previous lectures, right? Previous lecture decomposition, right? Singular value decomposition, eigen decomposition, etc. Look, this V1 has got to be maximized. Equivalently, I can say, because this Wi transpose and Wi, that product of a vector by itself leads to 1. Because I can put it as V1 equals this W1 transpose, yes, a covariance matrix, and a W1 divided by W transpose, whereas denominator is unit 1, right? Equivalently, I can put it. Look, this quotient is what is called Rayleigh quotient. This Rayleigh quotient has got to be maximized. The standard result for maximizing any Rayleigh quotient, especially for the matrix of type S, where S is XTX, any matrix of this nature XTX, which is a positive semi-definite, then the best maximum possible value is the eigenvalue of this matrix. Yes, this must have been discussed in morning lecture today, if not yesterday lecture, right? Look at whenever we are talking about Rayleigh quotient, that ratio can be maximized or that maximum possible value for such a Rayleigh quotient ratio is the eigenvalue of that matrix. If that matrix happens to be a positive semi-definite, then what I got to do is I expect this V1 to be equivalent to largest eigenvalue of that S. To be the largest eigenvalue of that S, because that is the maximum, then this W1 is nothing other than the eigenvector of this S corresponding to this largest eigenvalue. I mean,
Hello. Hello. Sir.
second principle is the direction of the eigenvector corresponding to the second largest eigenvalue. And if you want third principal component, go with eigenvector corresponding to the third largest eigenvalue. And if you want the D basis vectors, see that you just end up selecting first D eigenvectors based on the respective eigenvalues. The algorithm is so simple that take the data sample, compute the mean, subtract the mean from each data sample, and then go with the data normalization by dividing it by the standard deviation so that all become normalized to 0 to 1, and then compute the covariance matrix. And for that covariance matrix, you do eigen decomposition. That eigen decomposition gives you the eigenvectors. Those eigenvectors get sorted based on the eigenvalues according to their decreasing order. And now, if you want 10 dimension, choose the first 10 eigenvectors. If you want, 20 dimension, choose the first 20. If you want only 2, choose first 2 eigenvectors. And that eigenvector that you selected becomes a weight matrix. And now, project your data matrix X onto that projected. Whatever the W here, the W is nothing other than a collection of eigenvectors of the covariance matrix of this data matrix X. And obviously, because it is of n dimension, this you end up with n eigenvectors. You need not have to go with all n eigenvectors. You just go with only few in the beginning, right? D number of eigenvectors the moment you get them sorted according to their respective eigenvalues. This is how the principal component works, the algorithm for it. Right? That doesn't mean that PCA would help you in solving all problems, right? PCA has got its own shortcomings. PCA doesn't look at the class labels of the data samples. And if you look at this picture, obviously, this is the direction with which you have a degree of variance, right? Max matrix. But the moment you get these points projected onto this straight line, this direction, then you will get the samples of class 1 mixed with the sample of class 2, because this data get pointed over here, this data gets projected over here, and this gets projected over here, this gets projected. All the samples of class 2 gets mixed up with the samples of the class 1 the moment they are projected. But PCA doesn't help you in discriminating class 1 from class 2. Then you are going to go with a alternative version of this PCA, which takes into account what is called class label. That is what is called Fisher's linear discrimination. Look, indirectly what I am telling you is that PCA is an unsupervised learning algorithm. It doesn't take into account class labels, whereas Fisher linear discriminant or linear discriminant analysis, LDA or FLD, that is what is called a supervised learning algorithm. Supervised learning algorithm means that while computing the covariance matrix, it takes into account the class labels. Then the FLD or LDA first compute intra-class covariance matrices and also computes inter-class covariance matrices and takes the ratio of both of them, right? I mean, take the inverse of one and multiplies it, it becomes one covariance matrix, and then it goes with eigen decomposition of that combined covariance matrix. FLDA works better than PCA if you have information also. I mean, if your population is supervised population, I would recommend you to go with FLD, or if your population is unsupervised population, you go with what is called PCA. Look at here. So this is class 1, this is class 2. This direction is generated by PCA, but unfortunately, the moment these samples have been projected onto this dimension, this direction, or this single dimension subspace, then all get mixed up. You cannot discriminate. On the other hand, instead of projecting onto this line, if you project it onto green line, this direction, look at all these dots gets projected over here, and all these got projected over here, all these red dots gets projected over here, so that you can put a threshold. Anything above this is a class 2, anything below is a class 1. Then you have to generate this as the primary, this is the first principal component, not this. But unfortunately, if you run PCA on this data sample, then PCA gives you this as the first principal component, where you would utterly fail. Whereas in the case of FLD, you go with the FLD, because it takes into account class labels, it will give you this as the first principal component, so that class separability is possible, right? And number 2, irrespective of whether it is PCA or LDA, because they are linear transformations, they don't take into account non-linearity in the data. Then you have to go with project them to higher dimension. Look at, if you really want to segregate these samples into multiple classes, then PCA doesn't work, FLD doesn't work. Then you cannot think of reducing it to a single dimension. So it is in 2D. Initially, what you have to do is, suppose if this is 1 and this is 2nd and these are 3rd, and from here these are the samples of 4, from here it is the samples of 5 classes, then what you have to do is you have to unfold it. And I mean, it's like a curve, it's like a curve, you just unfold it. See that these points have been unfolded and placed on a single line. That unfolding can be possible if you move on to a kernel functions, right? And we have varieties of kernel functions in variants of PCA, kernel PCA. You can use those kernel PCA. Kernel function does the following. It takes you from lower dimension to higher dimension and then brings you back to a lower dimension. That's the basic philosophy of kernel PCA. Right? With this, if I sum up my lecture, friends, I just started with the general notions of dimensional reduction and then touched upon various methods of feature selection, right? And basically to filter and wrapper and their hybridization and ensembling, and particularly PCA as one of the feature transformation. And in between, I also explained how well we can exploit the beauty of quadratic equation solver as a feature reduction technique, because it generates a pair from a triplet. So 3D to 2D with some couple of examples. Hope I made this lecture more appealing for you and you understood. So opinion says that there is always a distance between two living things. There is always a distance between two living things. Otherwise, we don't say they are two, right? As it is unlikely that any two living beings are alike. It is even true with artificially made objects, however they are visually alike. If you keep this message in mind, I am sure that it is your responsibility. It is the responsibility of a feature selection, right? To dig out such features which make them different, right? Look, twins, two kids appear to be resembling same, looking same, right? But at least, if not everyone, at least mother of the kid is capable of distinguishing those two kids. I mean, mother remembers something which differentiate. I mean, out of all possible parameters, out of all possible n dimensions of those two kids, mother remembers only few, which helps her in discriminating kid 1 from kid 2. And that is what we are going to look at in case of feature reduction. So with this, let me acknowledge the organizers of this program for having extended an invitation for me to be with you all to spend about 90 minutes. And special thanks to Professor T.N. Nagbhushan, who was very particular in me engaging 1 or 2 sessions. And I must thank my research students who had given me a rich experience in this field of machine learning in general and dimension reduction in particular. I thank you one and all. Thank you very much. I would love to address a couple of points for clarification, if any.
Yeah, that was a very impressive talk, sir. Thank you very much for delivering us a very plethora of knowledge in the field of dimensionality reduction and PCA and many other tools. So, if audience, if you have any 1 or 2 questions, sir will answer that. Any questions?
I have one question, sir. Can I proceed?
Yeah, please.
Sir, thank you, Guru sir, for your very superb delivery of this session. To be frank, I'm very new to this dimensional direction, and now I can say that I know the basics of it from after your session. Sir, I
Yeah.
just want to ask you one question, sir. So you told me one method of grouping the features, like making K clusters. So if we are selecting randomly one feature from each cluster, suppose from K clusters, I'm just taking randomly one feature from each cluster. So K features, I will be selecting it. So in that case, is that randomness will affect the accuracy of the algorithm, or is there any other method after selecting the K feature? Is there any other method to again to say that which will affect the accuracy of the learning algorithm?
Yeah.
The
So one
randomness will
is
affect the
correct.
algorithm.
From each cluster of features, you end up selecting randomly one of them, right?
Yes, sir.
Yeah. So once you got the random selection of K features, then you try with a learning model, evaluate its success, and if you are unhappy, then you can selectively choose only few out of K also. Okay.
So few out of cases, then even we
Yeah,
can
you
reduce
can
the
further reduce
complexity.
it. You can further reduce it because even in the K features, there may be some feature which is misleading the classifier.
Okay, sir. Okay.
Okay. Then
Okay.
generally in classification we say that as and when you add up a new feature, classifier performance will improve. But it continue improving till some stage, and soon after adding next feature, that added feature may be a confusing feature, right?
Yes, sir.
Right? Again, you have to find out, is there any feature really confusing the classifier in discriminating samples of different classes? If you could identify such a feature, you can eliminate it. Right? Okay.
Okay. So then, sir,
So
in
you
from K
can look
features
at
are
in this
selected.
way. Yes. Look
Okay.
at in
So,
different ways, right?
okay. So is it
There is nothing like
certain
a
time?
standard way of solving a problem. It all
Yes,
depends
sir.
on the empirical analysis, right?
Okay, okay, sir. So then after K features, shall we apply this any kind of wrapper method like elimination or filter method, and
Correct.
we can just minimize it so that which
Yes.
will improve or reduce the accuracy of the algorithm.
And
And
sometimes you
if
can also
some
go with that. Sometimes you can also go with what, instead of choosing exactly one feature from each cluster, you can select multiple representative from clusters depending on the cluster size.
oh, okay, sir. So
After
everything is
clustering,
trial and error.
one cluster may have only 10 samples, only 10 features. Another cluster may have 100 features, right?
Yes, sir.
Yeah, instead of
Oh,
choosing only one from 100, you can choose 2 from 100, right?
oh, yes. So based on the density of the cluster, we can choose the number
Correct.
of
Based on the
features.
density and geographical coverage in the vector space. Okay, you can calculate the radius of that cluster and diameter of the cluster and then decide.
So then we cannot say any specific process for
No, there is
specific
nothing like a
method.
hard method of solving a problem. That you have to
Okay.
study depending on the data population.
Oh, so everything is like trial and error. No, so just we have to apply
Not like a
the
trial,
case.
not like a trial and error. If you give me the data set, probably I can straight away recommend which works reasonably better.
Based on your experience, you can just tell.
Yes,
that
yes. Look at the way in which the doctor prescribes a medicine for a patient, though it has to be trial and error, but experience guides,
Yes, sir. Yes, sir.
Exactly that. Exactly.
Yes, sir. But for a basic learner, we have to apply and we have to just experiment and then we have to
Like
see.
you, for a beginner like you have to try out better because that makes you rich experience.
Your voice is breaking, sir.
Hello?
Hello?
Audible?
Sir, no, sir.
Hello,
Your
am I
voice.
audible? Hello?
The voice
I can hear you. I can hear you.
now it is okay, sir. Now it is. I
Yeah,
think
yeah.
network is okay.
Yeah, for a beginner like you, I recommend you to try out with all possibilities and then learn a lot better, right?
Yes, sir. Yes.
So
Sure,
my
sir.
message to the budding technocrats, budding researcher is that please don't target on somehow getting the good results,
Yes.
right?
Yes, sir. Yes.
Try out with all possibilities because it makes you an experienced personality.
Yes. How
Okay.
many errors we get, we try to learn and
Correct. Right. You're right. Yeah.
Thanks a lot, sir. Thanks for your
Fine, madam.
concern and thanks, sir.
So there's one more question in the chat box. Can you say something about whether dimension reduction depends on the properties of data?
No, here what properties he is looking at, that's more important. So the moment I got the features extracted and represented in a real space, then there is nothing like properties associated. Everything is a real number for me, right? That's what I said in the beginning. Unless I am capable of associating each dimension with a semantic attribute, everything appears to be me a linearized, a sequence of real numbers. Hello?
Yeah. Yes. If there are any more questions, I mean, you can contact Professor Sir with his mail ID. So that was again, I wholeheartedly thank Dr. D.S. Guru Sir for his wonderful talk, and that was really a wonderful session, and the audience have gained a lot of knowledge in the area of dimensional reduction and PC and other techniques. So thank you very much, sir, for your time and your talk. So thank you from on behalf of HJC and the audience here. Thank you very
Thank
much.
you very much. Thanks a lot. Thank you.
Thank you, sir. The participants can join for the next session at 3 p.m. In the same link. So we'll join back at 3 p.m. again. Thank you very much.
Shall I leave?
Yes, sir. Thank you. Yeah, you can leave, sir.